Welcome to solverfy.
In this problem, we have a block in a jar of liquid that's suspended from a spring, and that's something basically that looks like we can draw it schematically as like ground, a spring, a block, a dash pot, and then ground. So we have something that looks like that. And in this case, we're told that the damping coefficient is 0.7, and that the units are pounds seconds per foot. The stiffness of the spring is 53 pounds per foot, and the mass of this block is 12 divided by g, and this is slugs or pounds seconds squared per foot. Now, we can find the natural frequency. Take this divided by this, and I've divided by my g here. And we get that that's 11.9 radians per second. We are told that this system was given an initial displacement of 0.62 feet and then released from rest, so the initial velocity is 0. Now, the damping ratio is c divided by 2 times the square root of km, and that's 0.7 divided by 8.89, and that's obviously less than 1. So this is an underdamped system. So we can find our damped natural frequency, and it is also 11.9 radians per second. Now, it's actually a little bit less than this, but if we round off the 3 significant digits, we get the same value. And that's because this damping coefficient is, this damping ratio is pretty small. So that's, when this number is small, this is very close to this. Now we know we need zeta times omega n, and we can calculate that as 0.939 because we need that for this exponential term. So we have the response is given by this equation. At t equals 0, we have d sine of capital phi, the phase, and that has to be 0.62 feet. Now we have the initial velocity, and again, you need to take a time derivative of this, and you need to use the product rule, and things get ugly. But in the end, when you plug in t equals 0, a lot of things drop out or things go to 1. So in this case, we get d times this quantity here. And now, if d is 0, then we have the trivial solution, and that basically y is 0, and then we can't meet our initial condition here. So d can't be 0, so we can divide through by it. And then we wind up with a tangent function, and we can take the inverse tangent, and we get that phi equals 1.49 radians. And once we know phi, we can plug that into here and then solve for d, and d becomes 0.622 feet. And then we can plug everything back into our response function, or the equation governing the response. So here's d, and this is zeta times omega n, so minus zeta omega n t, times sine of the damped natural frequency, which is 11.9 times t, plus the phase. And this would be in feet.